over here is our L minus A. And over here, exactly at the end, is our point A. Okay, so if I go into our moment diagram, okay. So this is our bending moment diagram. This is 0. This is A. This is L minus A. And this is my L. And this is my X distance. Okay, so all these are my X distance. Sorry, this is L, not A. Okay. Now, why geometric datum is always on the left-hand side, right? Because in our shear force and bending moment diagram, 0 is always on the left-hand side. Okay, so this is why, for this fact, this is why the geometric datum is always fixed. We are forming the equation based on the reference, have a fixed reference based from the geometric datum. That's why 0 is always on the left-hand side. That's why any analysis that you do, your geometric datum is on the left-hand side. That's the only reason. Okay, now let's look at the shear force. So the shear force at point A is minus P. Okay, so I'm going to call this my minus P. So let's do the shear force diagram first. Okay, and along A to B, right? Along A to B is also minus P. Okay, so it's minus P all the way, right? And then when we reach, okay, up to before point B, okay, it comes to here. Okay, but at point B, so basically when x equal to A, this is point B, this is point C, and this is our point D. Okay, I'll label this A, B, and C. Okay, so this is our point A, our point B, our point C, our point D. Okay, so from 0 to x, okay, it's still at minus P. So this is our shear force diagram. Okay, but however, at point B, right, you have the omega over 2 L bracket L minus 2A, and it's positive, so it's going to go positive. Okay, so it's omega over 2, right, L minus 2A. So it's going to go positive. So we have formed our shear force diagram up to point B. Okay, now if we look at the other equation, okay, our bending moment at point A is equal to 0. At point A is equal to 0. Right, so this is our 0. Then it goes to where? Minus px. So you know that minus px is negative slope, yes or no? Okay, so minus px. And then at point A, it stopped at minus pa. So you just select a point over here. This is minus pa. Okay, and this slope that we are drawing now, right, is expressed as minus what? Px, right? So minus px means it's a linear equation, negative slope. Yes or no? So this is equal to minus px. So we can draw up to here now. Okay. Now the next one is not difficult, but there are more factors involved. Okay. Any questions so far? So I think drawing this like based on the equation is simpler. Okay. Now, some of you can do this based on experience. By just looking at it, you can sketch the shear force and bending moment diagram. Good for you. There are a lot of students down here that don't have the experience, so that's why we are basing on the math and the physics of it. Okay. So the next thing that we're going to do now is we're going to do from point B to point C. Okay, that's where things get more difficult. I'm sorry, more complicated, but not necessarily difficult. Okay, so from point B to point C now. Okay, so our limits is A, X, L minus A. Okay, so now we have a more factors to consider. Okay, so this is our point A, and over here is our point B. Okay, then now you know why the geometric datum is always here. Okay, so from here to here, from here onwards, this is our X. Okay, this is our X. So immediately write down positive shear V as a function of X, positive bending moment M as a function of X. Then you put in your load. Over here, you have P. At point B, you have P plus by omega over 2 L minus 2A. Okay. Now, from B to X, there is a uniformly distributed load. Okay. I repeat again, there's a uniformly distributed load. Okay. So this uniformly distributed load is starting from point B onwards. Yes. And you have a load down here. Okay, from here to here. So this is going to be omega. But what is the distance? Right? What is that distance? Okay. So before you construct the shear force and bending moment equation or do static analysis, you need to get your forces right, which we have, and you have to get your distance right, which is what I'm teaching you now. Okay. So how to get the distance? How to get the distance right? Okay. So we know from here to here, this is A, right? So from here to here, the distance is equal to X minus A. Okay. So the evenly distributed load, to multiply the distance, this from here to here is X minus A. Okay. Now, which is the distance that is more critical? Okay. So it's from here to the end. Okay. This distance is more critical because later on, we are going to take moment at this point, right? Relative to omega X minus A. So from here, we know that this distance is equal to X minus A divided by 2. Because it's evenly distributed load. Okay, let me help you do a recall. If you have an evenly distributed load, and the distance from here to here is A, and this is omega, right? The equivalent load, when you construct your free body diagram, this is omega A, right? And from here to here is A over 2. And this is why our distance expression is like this. Okay. So get your distance right, or get the distance right. Very important. You get the distance wrong, we are game over. Your shear force diagram might be easy. Your bending moment equation will be wrong. Okay. Then again, we carry out static analysis. Yeah, we carry a static analysis. So positive. So there are more factors to consider now. Okay. So you have minus P plus by P plus by omega over 2 L minus 2A. Okay. Then minus omega x minus a minus b as a function of x. The whole thing will be equal to 0. Okay. So you can get rid of this. You can get rid of this. Okay. So I'm going to express as b as a function of x now. Right. So this is equal to omega x minus a. Right. Wait. Sorry, it's still minus because I bring Vx as positive now. So it remains the same. So it's omega over 2 L minus 2a minus omega x minus a. Okay. So you remove the bracket, omega L over 2 minus by omega a minus by omega x plus by omega a. You get rid of these two terms over here. So you have minus omega x plus by omega L over 2. Okay. So that is your equation for your shear force diagram. Okay. And the limits is from A to L minus A. Next, where it gets a bit confusing, but does not mean it's impossible, is we're going to do the moment. Okay. Now this is where you have to get your distance right. If your distance are wrong, okay, whatever you form, game over, no point. Okay. So will be equal to summation about moment, the z-axis, about the z-axis anywhere at point x. Okay. Again, I'm going to repeat myself. We are taking moment at the red dot. Okay, you are taking moment at the red dot. So the first one is going to be px, p multiplied by x, and it's going in an anti-clockwise direction, so it's positive. Then you have minus, right? Minus p plus by omega over 2 L minus 2a. And then you include the distance x minus a. Okay. And then the next one is plus omega x minus a multiplied by x minus a divided by 2. Okay. And then you do plus by m as a function of x. Quite a long expression, but not impossible to solve. Okay. So now you just need to open up the brackets. I'm going to use down here. Okay, I'm going to scoop over to use this part of the page. Okay. You know what? Forget it because I need a lot of space. Okay. So I'm going to go to the next page. So this is just, I won't say just map. You have to be really, really careful over here. Okay. So I'm going to, so this is px. Minus by p x minus a. So minus and plus is minus, right? So minus omega over 2 L minus a x minus a. Okay. So that as I said, you have to be really, really careful over here. So plus by omega over 2 x squared minus 2ax plus by a squared. So the whole thing plus by m as a function of x. Okay. So px minus by px plus by pa. minus omega over 2 Lx minus by La minus by Ax, okay, plus by